Hello again, and welcome to Day 7, Lecture 1. In this lecture, we're going to be talking about blood pressure regulation, and specifically, we're going to be talking about neural regulation of blood pressure. So that's short-term regulation via the nervous system. Okay, let's go. Then accompanying this lecture will be worksheet 7.1. All right, few memes here. Up in the top left, this one was actually created by a student last year. Apparently, they were studying off one of my old PowerPoints for an exam the next day, and they thought and admittedly, that is a copious amount of spelling errors, and they thought that was a little unfair, and perhaps that would warrant a free point on an exam should it cover that slide's topic. But I think I've corrected that slide now. Top right, we got teacher, copy these notes carefully, they'll be on the test, and then 5 seconds later they're erased. And then another student submission here in the bottom right, because my name is Trevor, someone thought this was pretty clever. First, we're going to look at how the cardiovascular center, which includes the cardiac center and the vasomotor center, help regulate blood pressure. Well, first off, why regulate our blood pressure? Well, it's got to be kept within a proper range, and that range would be high enough to maintain adequate perfusion of our tissues. We've got to be able to drive blood into those tissues where we need nutrients and gas exchange, but not so high as to damage those vessels that are transporting the blood. Now, a student asked last year, what's the danger of high blood pressure? What does that do over time? Well, it's going to damage those arteries. High blood pressure can damage the cells that line the arteries, right? The endothelial cells. And then fats or cholesterol within your diet, when it's in the bloodstream, that can then collect in those damaged areas. And we've spoken previously of the dangers of the formation of a thrombus or a clot. Additionally, over time, high blood pressure can affect the ability of the arteries to dilate or constrict. So if your blood pressure is too high, the muscles in the artery wall, they're going to respond by pushing back even harder. And we've spoken about that previously, the myogenic response. So that's that contraction, relaxation, the smooth muscle within the artery walls if there is increased or decreased stretch within that vessel wall. So what happens is with high blood pressure, the arteries are going to respond by pushing back on that blood, and over time, that's going to make them grow bigger, right? Because the artery walls are going to thicken due to that increase in the smooth muscle cells that are constantly pushing back on that blood. And what that does then is it increases the wall thickness, which is reducing the interior diameter of that artery, right? And we know the smaller diameter, that's going to increase resistance, and it's kind of like this positive feedback loop. And that is going to further increase your hypertension or high blood pressure. Blood pressure depends on 3 main variables. The first of those is going to be your cardiac output, or CO. And remember, that's the amount of blood pumped by the heart within 1 minute. Second, the resistance that blood encounters as it's moving through the vessels in your body. And then third, how much blood is present. That's the blood volume. Now, these variables are regulated by the nervous system, which is short-term regulation of blood pressure, or the endocrine system we'll talk about in the next lecture, which is long-term regulation of blood pressure. Short-term regulation of blood pressure occurs through autonomic reflexes. And remember, autonomic functions are those that occur automatically, or at least on a subconscious level. So here in the bottom right, we have this woman who's seated and then stands up quickly. And what she's demonstrating, oftentimes I'm sure you're familiar with this, where you've been laying on the couch a long time and then you stand up quickly and you get really dizzy. So that's orthostatic hypotension, meaning ortho means straight, so you're standing straight up, and then hypotension, low blood pressure. So it's when gravity causes the blood to move to your legs and your abdomen real quickly, and then you feel lightheaded. So as a think, pair, share, what must happen to our blood pressure when we move from that sitting to standing so that we don't pass out, and how is our blood pressure adjusted? So think about that for a second. Well, what we see here is that our autonomic reflexes help meet the momentary pressure needs. So we're standing up, and that gravity causes the blood to rush to the lower part of our body. Well, we need to compensate for that. So we're going to quickly adjust our cardiac output and our resistance, or both. And remember, the third determinant was blood volume, and we can't really change our blood volume rapidly. So what we do in this case, for example, we stand up quickly, is our heart is going to beat stronger. That's going to increase blood pressure, get the blood up into our head. It's going to beat faster, also help with that. And then our arteries and our veins are going to constrict. Okay, that's going to increase resistance, which is going to increase our blood pressure. Get it up into the head. Okay, and these reflexes, they involve nuclei within the medulla oblongata. Now, last semester we talked about the nuclei within the medulla. So just a reminder, that's part of the brainstem. That's the lower part of that brainstem there, the medulla. There are two groups of autonomic nuclei within the medulla oblongata that help regulate blood pressure. And those are the cardiac center and the vasomotor center. And collectively, we call these the cardiovascular center. First, we have the cardiac center, and this changes blood pressure by changing cardiac output. And we have both excitatory and inhibitory components of that cardiac center. So there's a specific cardio-oscillatory center and a cardio-inhibitory center. And then we also have the vasomotor center. And this is going to change our blood pressure by changing the vessel diameter. So for example, constriction is going to influence resistance. We constrict, there's going to be higher resistance within that vessel on the blood. First, let's look at the cardiac center, of which we said had both the cardio-oscillatory and cardio-inhibitory centers within the medulla oblongata. Let's start with cardio-oscillatory. Okay, so we can see arising then from the brainstem, the medulla oblongata, we have a preganglionic sympathetic neuron. Remember, our sympathetic neurons and parasympathetic neurons were two neuron chains with that autonomic nervous system. So we have a preganglionic neuron here, and then we have a postganglionic sympathetic neuron shown in green. And specifically, we're talking about the cardiac nerve here. So this is the sympathetic nerve. And notice that cardiac nerve goes on to innervate the SA node and the AV node. And with that innervation, we see an increase in heart rate. But also notice that we get those sympathetic neurons, the green here, they go into the myocardium of the heart. Okay? And therefore, we see an increase in the force of contraction. Okay? So if we think back, we know that cardiac output is a component of heart rate. So I'm going to do HR by stroke volume, SV. And that equals our cardiac output. And we've just increased both those components. We've increased heart rate with this innervation to these nodes, and we've increased our contractile force by the innervation to the myocardium. So we get release of norepinephrine from these sympathetic neurons, and they increase these two factors. So we increase our cardiac output. And we just said at the start of this lecture that cardiac output is one of the determinants of blood pressure. So via this cardio-oscillatory center, we've effectively increased our blood pressure. To recap, we've seen that sympathetic signals from the cardio-oscillatory center and the medulla, they'll travel via sympathetic nerves, specifically the cardiac nerve for that postganglionic nerve. And there they're going to release norepinephrine at the heart. The norepinephrine that's released at the SA node of the heart is going to increase the rate of firing. Okay? And that's due to the increased rate of depolarization of the nodal cells. And we'll look at that in a second. And we'll also see reduced delay at the AV node. Remember, there's that slight delay that allows the atria to completely empty before the ventricles contract. So that's going to be quickened, a reduced relay there. And we've also seen that there's going to be an enhanced contraction due to sympathetic innervation of the myocardium. But first, let's turn to these effects on heart rate. We said then that norepinephrine release at that SA node from that cardiac nerve, the sympathetic fiber, is going to lead to increased firing rate. Well, let's just quickly review how that happens. So if we have that cardiac nerve here, we're releasing this norepinephrine. The norepinephrine binds to a beta-1 adrenergic receptor. So you're going to have to think back to last semester when we talked about the different adrenergic receptors, and we said that beta-1, those were found in the heart predominantly, and they were excitatory, being adrenergic. So we bind this excitatory beta adrenergic receptor, and that's going to activate this G protein coupled receptor here. Okay? And ultimately what we do is we phosphorylate a calcium channel. When we phosphorylate that calcium channel, we increase our calcium influx into the nodal cell, and with that increase in calcium, that cell fires sooner. Here's shown sympathetic stimulation of a nodal cell. So the regular depolarizations would be shown with this black dash line of the nodal cell, so under regular circumstances. Now with sympathetic stimulation, that is this blue line that is shown here, and you can see we've increased the number of depolarizations in a given time frame. So that increased rate of depolarization is due to a quicker drift to threshold. So remember that that is caused by sodium channels opening, the funny channels, and then these calcium channels, type T calcium channels. And we just saw that with norepinephrine released onto nodal cells, we will get more influx of calcium here so that we can reach threshold more quickly, leading to more depolarizations over a given time period. And we also said that we'd see enhanced atrial and ventricular contraction, sympathetic effect due to that norepinephrine and the innervation of the myocardium. So let's just quickly revisit that mechanism. With the myocardium of the heart, the norepinephrine leads to prolonged opening of L-type, or long-lasting calcium channels. And with that increased influx of calcium, we get stronger contractions. There's more calcium to bind troponin, those myosin binding sites are exposed longer, and we get stronger contractions. Again, if we increase our stroke volume, we're getting stronger contractions, we're going to have higher stroke volume, we're going to see an increase in cardiac output, and an increase in cardiac output leads to an increase in blood pressure. Now that we've reviewed the cardiooscillatory center with the sympathetic effects, let's look at the cardioinhibitory center within that cardiac center of the medulla. So now we see these orange fibers leaving the cardioinhibitory center. These are parasympathetic fibers. And remember with parasympathetic, they're going to have a long preganglion and a short postganglion. In fact, it's so short here you can barely see these on the images. So long preganglion, short postganglion. Here they're showing both the left and right vagus nerves, so left and right. And remember with the vagus nerve, this is where we slow activity of the heart. So with these fibers here, we're going to be releasing acetylcholine, and that parasympathetic activity is going to act to decrease heart rate and slow conduction of electrical signals in the heart. So ultimately, we're going to decrease cardiac output and therefore decrease blood pressure. And parasympathetic stimulation of the heart is going to be pretty much the opposite of sympathetic. So with acetylcholine release now, we're going to see a decrease firing at the SA node. So that's going to prolong that drift to threshold. And then we're going to see an increased delay at the AV node. Now, there was no innervation of the myocardium as there was with the sympathetic innervation. So we're not going to see an effect on the contractile force, just the heart rate. One of the actions of acetylcholine will be to increase the drift to threshold for a nodal cell. So we'll see that acetylcholine will bind a muscarinic receptor that ultimately opens a potassium channel. The potassium then exits that nodal cell, making it more negative, moving it further away from threshold. So it's going to take a longer time for that nodal cell to reach threshold, which means ultimately we're going to have a slower heart rate. If this black line represents the normal nodal cell activity depolarizations, then this red line is going to indicate the parasympathetic stimulation, the effect of acetylcholine. So that'll be the opening of those potassium channels, and we'll have increased potassium permeability. So we're going to hyperpolarize the SA node then, and that's because more positive ions are leaving, making that inside more negative. So we're going to elongate this drift to threshold then if this internal environment of that nodal cell is more negative. We'll now switch from the cardiac center to the vasomotor center. Back within this cardiovascular center, we have the vasomotor center, and this sits superior to the cardiac center that we just finished up with. And the vasomotor center is origin of sympathetic pathways. So now we can follow this purple line here, this short preganglionic sympathetic fiber, and then we have these long sympathetic postganglionic fibers. And these lead to our blood vessels where they're going to release norepinephrine. Now, sympathetic activation also stimulates the adrenal medulla. Think back to the first semester, you had block, to release epinephrine and norepinephrine as hormones into the blood. Now, unlike the heart, the vessels do not have dual innervation, so we're going to see only sympathetic effects here. These vessels are innervated only by sympathetic division, and whether we get dilation or constriction is going to be dependent upon what type of receptor they have, either alpha-1 receptors or beta-2 receptors, but there is no parasympathetic innervation for these vessels, for the most part. And we'll now look at the difference between alpha-1 receptors and beta-2 receptors in regards to vasodilation or constriction. Whether a vessel dilates or constricts in response to sympathetic innervation is going to be dependent on which type of receptor it has within the tunica media. And remember, the tunica media is that layer, the middle layer of a vessel made up of the smooth muscle arranged in that circular fashion, so we can change the diameter of our vessel. So we can have either alpha-1 or beta-2 receptors, and the receptor subtype is going to be specific to the location of the body and specific to a certain type of tissue. We'll begin by looking at the alpha-1 receptors, and these are found within the smooth muscle cells of most of the blood vessels in the body. And sympathetic stimulation from the vasomotor center of the medulla would lead to vessel constriction for alpha-1 receptors. So we can say that for most blood vessels, a sympathetic response leads to vasoconstriction. And we'll look at why this is important shortly. Beta-2 receptors then, when stimulated via sympathetic response, are going to vasodilate. And most beta-2 receptors dilate in response to epinephrine, not norepinephrine, as we saw with the alpha-1 receptors. And recall that epinephrine is released as a hormone into the blood by the adrenal medulla after a sympathetic stimulation. Let's take a look at the overall impact of sympathetic division activation. Okay, I want to take a minute and check for understanding so far. So pull out a scrap sheet of paper here. I think this will be helpful. And think of how activation of the sympathetic division, that includes the stimulation of the adrenal medulla and the epinephrine hormone release, how that would affect the three following things. So we're talking about resistance, circulating blood volume, and blood flow to skeletal muscle and heart, given sympathetic activation. And I should point out that at the start of this, I said total blood volume doesn't change quickly, but your circulating blood volume can be adjusted. All right, maybe you humored me and we can check your work here. So the first thing I asked you to think about was peripheral resistance and how that would change with sympathetic activation. Well, what we see is increased peripheral resistance. And that's because there are more vessels that have alpha 1 receptors. Remember, we said that the majority of smooth muscle in your vessels has alpha 1 receptors. So we would see then that constriction would cause an increase in resistance, more friction as that blood's moving through that narrower vessel. And that's going to increase your blood pressure. The next item was your circulating blood volume and how that could change given a sympathetic response. And what we find is there'd be a larger circulating blood volume. And the reason for this is that vasoconstriction, that's going to move blood out of those venous reservoirs. Remember we said your veins, one of the things they can do is act as a reservoir for blood. So with vasoconstriction, we're constricting those, pushing blood into circulation. Your circulating blood volume is going to increase, and that's going to also increase your blood pressure. And the last thing I asked you to consider was how redistribution of blood flow would change. And specifically, I asked you about whether it'd be more or less blood flow to the heart and skeletal muscle. Well, I was particularly vague earlier when I was talking about the beta 2 receptors, because I wanted to ask you this question now. And these structures, the heart and the skeletal muscle, they contain beta 2 receptors within the smooth muscle of their vessels. So these are a few of the vessels that would dilate with sympathetic activation. And when those vessels dilate, that means more blood flow to the heart and skeletal muscle. They're going to need more oxygen and nutrients for a sympathetic response, a fight or flight situation. And we're also going to see simultaneously constriction with the majority of the vessels elsewhere in the body, and less blood reaches those areas that are less essential for that fight or flight response. So we're talking here about your coronary arteries that supply the heart, those are going to dilate, and then the vessels supplying your skeletal muscle. All right, and on to baroreceptors. You may have been asking yourself, well, what is it that's sending signals to the cardiovascular center within the medulla oblongata, specifically to the cardiac and the vasomotor centers? What is informing those centers about blood pressure conditions within the body? Well, that's the job of baroreceptors. These are specialized nerve endings that respond to stretch within a vessel wall. So that prefix baro means pressure. So with more pressure in the blood, we get more stretch of that vessel wall. And the firing rates are going to change from these baroreceptors with changes in blood pressure. And specifically, they're located in the tunica externa. So remember, that's that outer tunic of vessels of our aortic arches, or the aortic arch, I should say, and the carotid sinuses, so within the carotid arteries. We'll begin with the baroreceptors within the aortic arch. Okay. And we can see that leaving the aortic arch, we have the vagus nerve here indicated in blue. And that's going to go up to the brainstem, specifically into the medulla oblongata, where we have that cardiovascular center. Okay. And these are important, the aortic arch baroreceptors. They're important in regulating systemic blood pressure, so overall blood pressure within the body. Next, we have the baroreceptors within the carotid sinuses. So if we look over here at the carotid artery, we can see where it branches. We have baroreceptors within those sinuses. And these baroreceptors, they transmit their signals via the glossopharyngeal nerve. So I'm highlighting it here, and move up to the medulla. And these are going to be important for monitoring blood pressure within the head and the neck. So as you can imagine, then they're more sensitive to blood pressure changes than those baroreceptors that are within the aortic arch. So why do you think it's important for those to be more sensitive? I'm not going to spend too much time on this, but that's because they're informing about blood pressure within the head, and that's where your brain is, and your brain cannot ever go without oxygen. So for that reason, more sensitive to blood pressure changes, these carotid sinus baroreceptors. And finally today, the baroreceptor reflex. Now we're going to put everything together and talk about the baroreceptor reflex to finish up today. Those baroreceptors we just finished with, they're activated in response to changes in stretch of blood vessel walls, and they're going to initiate autonomic reflexes that are going to regulate the blood pressure. These reflexes we call baroreceptor reflexes, and they're initiated by decrease or increase in blood pressure. Time to apply your knowledge. So if you did print out your worksheet, go ahead and pull it out. This will be the first set of questions there. We're going to apply everything that we've learned today so far by looking at a couple different scenarios. Let's turn to the first scenario. Scenario 1, a very likely scenario, at least for me, maybe for you. You oversleep and quickly rise from bed in the morning. You feel lightheaded, but then your autonomic reflexes thankfully kick in. Describe the series of events, and you can write this on your worksheet if you printed it out, that would occur to increase your blood pressure, to counteract that lightheadedness or loss of blood flow to the head. Be sure to include both the cardiac and vascular responses and indicate the different receptor types that we talked about. Scenario 1 represents a decrease in blood pressure. So the first thing we're going to see is the vessel stretch will decline, and then those baroreceptor firing rates are going to decrease. So with a drop in blood pressure, there's going to be less pressure on those vessel walls, and there's going to be less stretch. Those baroreceptors that detect that stretch, they're going to send fewer signals up to the medulla oblongata. And this is going to be detected by both those aortic and carotid baroreceptors. The next thing we see is that signal is going to be sent via the vagus and the glossopharyngeal nerves to both the cardiac and vasomotor centers via their respective nerves. So for your aortic baroreceptors, that's vagus, and your carotid baroreceptors, that'll be sent via the glossopharyngeal. So those signals are going to activate the cardiooscillatory center to stimulate sympathetic pathways to increase heart rate and stroke volume. And we know that heart rate times stroke volume equals cardiac output. So we're going to increase our cardiac output. So we're going to see effects at the SA node, the AV node, and the myocardial effect with that sympathetic stimulation. Simultaneously then, we're going to inhibit the cardioinhibitory center, and that's to help minimize the parasympathetic response, and which has effects at the SA node and the AV node, but there's no myocardial effect as there is with sympathetic activation. At the same time, the vasomotor center is going to increase signals via those sympathetic pathways to the blood vessels, and that's going to lead to net vasoconstriction. While we will see some dilation, the overall effect, remember, is vasoconstriction because there's more alpha-1 receptors. Therefore, we're going to see an increase in peripheral resistance, and we're going to shift that blood from the venous reservoirs into circulation. The overall effect then is we're going to see an increase in cardiac output and resistance, which raise our blood pressure. Scenario 2, we just got a different scenario. This is if your blood pressure increases. Go ahead and work through this, and you can check out your answers on the next page. And we'll see you for the next lecture.